Swayam Prabha. Digital India. Educated India.
Hello, welcome back. We will continue with the torsion of shaft with thin rectangular cross section. In the last lecture, we have found out that the Prandtl stress function can be very well approximated by slightly approximating the deformed shape of the analogous membrane, whereby the approximated deformed shape does not depend on coordinate y and is constant throughout the y. With this assumption, we have found out the Prandtl stress function of this form. Now, from this Prandtl stress function, we will try to derive the expression for shear stress and the torsional moment. Now, as we remember, the shear stress in terms of Prandtl stress function is given as tau xz, which is del phi by del y, and tau yz, which is minus del phi by del x. Now, we know that the Prandtl stress function does not depend on y, therefore, this goes to 0 and we have only tau yz component. So, let us now find out what is tau yz. So, tau yz therefore is going to be minus del phi by del x, which is given as minus g theta into 2x. So, which is minus 2 g theta x. So, therefore, in the narrow cross section shaft, the predominant shear stress that we have is tau yz, and the expression for tau yz is given as minus 2 g theta. So, if I try to draw it, so we will have tau yz acting through the shaft, and this is tau yz, which is the predominant shear stress. Tau xz is equal to 0 because of the approximation we have made, but we are not losing much by this approximation because tau xz will act only in a small portion near the two ends. So, ideally, if we go by theory, tau xz will act only at a small portion near the two ends of the cross section, which is approximated to be 0. The effect of tau xz will be very minimum. So, therefore, the predominant stress that we have is tau, which is tau yz, and the distribution of tau yz is given as 2 g theta x. Now, if we try to find out the maximum shear stress, how do we find it out? So, the tau max, either by inspecting this expression, we know that tau max will occur at x is equal to plus minus t by 2. When x is max, tau, which is tau yz, is maximum, and that is going to give up the maximum value of the shear stress. So, tau max is going to be plus minus g theta into t. So, that is one way to find out the maximum shear stress. The other way is to by using the corollary of the membrane analogy. So, from the second corollary of the membrane analogy, we have seen that the maximum shear stress is going to happen at point which has the maximum slope. So, we can see from the deformed shape that at this 2 point there will be the maximum slope of the deformed membrane. So, therefore, the maximum stresses will act at this 2 point which has the maximum slope using membrane analogy. So, that is also corroborated from this expression. So, we can say that maximum shear stress maximum shear stresses occur where the membrane has maximum slope. And this we can visualize will happen at x equals to plus minus t by 2. So, either by inspection we can say this, or from membrane analogy we can say this. Now, let us try. So, we know that if we have a narrow rectangular cross section shaft, the maximum value of the shear stress is going to be g theta into t, where t is the thickness of the shaft. Now, let us find out the expression for torsional moment. So, the torsional moment mt can be written as 2 into phi into dx into dy. Now, we have seen that phi is 2 into minus g theta x square minus t square by 4 into dx dy. Now, if we try to integrate this, I have minus 2 g theta, dy is not changing. So, the integral of dy is going to be b, then we have minus t by 2, 2t by 2 into x square minus t square by 4 into dx. So, if we integrate this, we have minus 2 g theta into b into x cube by 3 minus t square x by 4, where t varies from minus t by 2 to plus t by 2. If we evaluate this integral, we will find out that this is going to be g theta b t cube by 4. Therefore, from membrane analogy we find out that mt is going to be g theta b t cube by 3, which can also be written as gj into theta, where gj is the torsional rigidity of the cross section. Therefore, torsional rigidity is given as gj, which is going to be bt cube by 3. So, therefore, the torsional rigidity of a shaft with thin rectangular cross section is obtained as b t cube by 3, where t is the thickness of the cross section. Now, let us see how we can apply this to different problems. So, let us consider a shaft let us consider a shaft so this is the z axis. So this is no longer the cross section of the shaft. Please remember that this is not the cross section of the shaft. This is x, this is y. So this is the torsional moment mt. So if I take a cross section of this shaft, so let me say that this is the shaft under torsion. So this is the shaft that we have, which is experiencing a torsional moment mt. Now I have taken an arbitrary section of cross section of the shaft, which is AA. Now let this cross section be the shape of a C. Okay, so this is section AA. Okay, so we let the cross section be the shape of a C. Many of us are acquainted with C section shaft, C section beam, and especially the students of aerospace engineering, you know that many of the stringer spars are made out of this such kind of C section, I section, Z section, and so on. So let us consider a C section. Let the dimension of the C section be given like this. So let this be B. Let this be A. Let this be A. Let this be B also. And let the thickness be T. Okay, so uniform thickness T. Now both B and A is much larger than T. So this is a shaft with thin walled cross section. Okay, so the C section is a thin walled section because B or A is much larger than the thickness T. So this is a thin walled cross section. Okay. Now if I need to find out the torsional rigidity, so the question posed is find the torsional rigidity of the shaft. So how are we going to find this out? So we are going to find this out in this form. We are going to take a cross section which has this uniform thickness T. Now the total torsional moment can be written as mt, which is going to be Gj1 into theta plus Gj2 into theta plus Gj3 into theta, where J1 is the thickness, is the torsional rigidity of this section, G2 is the torsional rigidity of this, and Gj3 is the torsional rigidity of this. Okay. So, therefore, but since this is a single cross section, it will have a single angle of twist which is theta. So, this can be written as Gj1 plus Gj2 plus Gj3 into theta. Okay. Now, again Gj1 is equal to Gj3 because they are symmetric, because it is a symmetric C cross section. So, therefore, this can be written as 2 Gj1 plus Gj2 theta. So, if it is made of single material, we can say this to be 2 J1 plus J2 into G theta. Now, what is J1 and J2? So, the J1 and J2 are basically, we have to now consider this as a rectangular cross section, thin rectangular cross section, and can be written as 2 into J1, which is B T cube by 3. So, this two portion can be considered as a cross section of thin rectangle with thickness T and the length B. Similarly, this portion can be considered as a thin rectangular cross section with thickness T and length C A. So, this can be written as A T cube by 3 into G theta. Therefore, this can be written as G theta T cube by 2 into 2B plus A. Therefore, the torsional rigidity of this cross section C section can be written as G 2B plus A T cube by 3. Sorry, this should be 3. So, this is the answer that we are looking for. So, given any thin wall cross section like an I section or open cross section, it should not be a closed cross section, it should not be a thin annular ring or a box or a rectangle or a square box. Those closed cross section we cannot obtain, but for any open cross section, it could be an I beam, it could be an I beam, it could be a jet section, it could be an L section, any section that we can think of, but open can be modeled using this concept. So, this shows that making a very small approximation without losing any considerable accuracy, we can obtain a very easy way to find out the torsional properties or torsional analysis of a shaft with thin wall cross section. If we have a shaft with any open thin wall cross section, we can very easily do the torsional analysis of that cross section. So, we are going to next solve a similar problem, another example, to further clarify the concepts of finding out the torsional characteristics of a thin wall cross section. So, we need to find out the torsional rigidity of the triangular isosceles triangular cross section shown in the figure. So, here also the idea of a membrane analogy will be used, and this is also can be treated as a thin cross section, because the height of the triangle B is much greater than the base of the triangle C. So, B is much more greater than C. So, here also we can assume that the deformed shape can be very well approximated by a corresponding shape, but neglecting corresponding flat shape, flat deformed shape, neglecting the end effect, or in other words, the deformed shape in the YZ plane is going to be very well approximated as this, and on this axis it could be very well approximated like this. So, this is x, this is z, this is z, and this is y. So, this is xz plane and this is yz plane. Now, using the similar concept by which we solve the narrow rectangular cross section, we can say that considering this approximate deformed shape. So, this is approximate deformed shape. We can say that MT, that phi, the Prandtl stress function, can be approximated as minus g theta into x square minus t square by 4, where t square, t is the width of the triangle at any y. Okay. The Prandtl stress function does not depend on y, does not vary with y, but the width t at any y can be is dependent on y. So, t is any depth. So, this is t, which is a function of y, which is at any arbitrary y from the base of the triangle. Now, this can therefore be written as minus g theta x square minus c square by 4 b square into b minus y whole square, is because t, which is a function of y, can be written as c by 2b into b minus y. So, this is how it can be, c by 2 by b into. So, therefore, by substituting this here, this is what we get. Therefore, the torsional moment MT can be written as 2 Now, by substituting the value of phi, we can write this as minus 2 g theta Therefore, this can be further, the limits of this can be written as minus 2g theta. The limit of y is from 0 to b, whereas the limit of x is from minus c by 2b into b minus y to plus c by 2b into b minus y. This is the limit of x that we have to consider, and then we have x square minus c square by 4b square into b minus y whole square into dx dy. Now this can be evaluated, this integral can be evaluated very easily, and it can be written as minus 2g theta 0 to b, and then we have x cube by 3 minus c square x by 4b square b minus y whole square minus c by 2b. So after imposing the boundary conditions, the limit, we can write this as c minus y and this as c by 2b b minus y. So if we evaluate this, this is going to be minus 2g theta 0 to b into b minus y whole cube dy by into 2 c cube by 12 b cube. And if this is evaluated further, this ends up being g theta c cube b by 12. Therefore, for this cross section, using membrane analogy, we can say that the torsional moment is g theta c cube b by 12. Therefore, the torsional rigidity can be written as Gj, which is g c cube b by 12. So this is the answer that we were looking for. So with this, I will end this lecture. In next lecture, we will be studying the torsion of thin wall cross section but closed. Thank you.